In this video we look at correlation coefficients and understand what they are and how to calculate them. So one of the purposes of analyzing data is to determine if one variable is affected by another. So we want to see if changes in one variable will make or cause a change in another. We're going to focus specifically on linear relationships here, and we say that there's a linear correlation between two variables if the changes in one variable are proportional to the changes in another. We can have several different types of correlations. So we can have a positive correlation, sometimes called a direct relationship. A positive correlation would sort of look like this. The idea is that as the dependent variable increases at a the dependent variable. I didn't do a very good job here. Let me fix that up. Let's try that again. It looked more like a curve than a straight line, so now it doesn't have to be perfect. The idea is that the trend is upward. So the dependent variable, so the y value, increases at a constant rate as the independent variable increases, or the x value increases. If we were to draw a line of best fit, it might go something like this, and it would slope up and to the right. So a positive correlation is a relationship that has a positive slope. Negative correlation is, as you might guess, the opposite of that, as the y value decreases as the x value increases. So we get something that looks maybe like this, with a line of best fit that looks like this. This is sometimes called an inverse relationship, because one value is going down as the other one is going up. In this case, the y value is decreasing as x is increasing. And the line of best fit slopes down and to the right. So those are two different types of correlations here that we can see for linear relationships. Now we can talk about the strength of a correlation. There are a few different words that we can kind of use to describe the strength of a correlation. So a correlation is perfect if all of the points lie perfectly on the line of best fit. So they go through exactly. That's what we call a perfect correlation. A strong correlation would have all of the points close to the line of best fit. It wouldn't be perfect. Some might be off by a little bit, might be up a little bit, down a little bit, but generally the points aren't too far away from the line of best fit. A moderate correlation is more spread out than a strong one, as you might guess, and for a weak correlation there is a trend, but the points are very spread out, and that trend it can be seen, but it's not quite as obvious that the relationship is as strong. And the last one here is that we could have no correlation. So there could be a situation where all of the points are just totally scattered randomly throughout the graph, indicating that there's no trend and there's no correlation between the two variables. So an example would be that right there. So this is all fine and good to describe a correlation, but then eventually we get to the nitty-gritty of, well, where's the line between perfect and strong and moderate and so on. So we need some number to describe this, and that number is what we call the correlation coefficient. We use the letter R to represent the correlation coefficient. It tells us how well the line of best fit fits the data. So if the data fits perfectly on the line, then we say that the correlation coefficient is 1 or -1, depending if the line is sloping up or down. We'll talk about that in a minute. So the values of R can range from -1 to +1. We'll look at an image here in a second. If the correlation coefficient is equal to -1, then we have a perfect negative correlation. So it's a perfectly straight line, and you can see this graph down here. I'm not going to draw it. It's perfectly straight, but you get the idea. That is a perfectly straight line. So we say that the correlation coefficient, so R, these are R values listed here. So R is equal to -1. If the correlation is perfectly positive, then we say that R is equal to +1. So this is the perfectly positive correlation. And then we kind of subdivide between -1 and 1 into the different points here. So we can have a strong negative correlation. So that would be a value between -0.67 and -1, or -1 and -0.67. We can have a moderate negative correlation, and that would be between -0.67 and -0.33. It's weak if the correlation coefficient is between -0.33 and 0. weak between 0 and 0.33, moderate between 0.33 and 0.67, and strong in this interval here. And you can see the kind of corresponding pictures that would go with that. I should mention that 0, if the correlation coefficient is 0, that indicates that there is absolutely no correlation whatsoever. No matter how hard you try, you can't find a line of best fit. So those are examples of correlation coefficient in use. We should talk now a little bit about how do we calculate the correlation coefficient. And we use this equation right here. It looks kind of long and tedious. We'll just break it down into little bits and steps, and we'll use an example to show that. So in this example, we're asked to determine the correlation coefficient of this data. In this equation, I should mention that n is the number of data points. The sum of the xy's basically means take your x values, so these are our independent variables here. Our dependent variable is over here. So we're going to take those x values and multiply them by the y values. So we'll make another column here that is the x times the y. So we'll have those, go through the process of calculating those. And then we also need the sum of the x's. So that's just the sum of this column, and we'll go through and do that. We need the sum of the y's. We have an n here. We need the sum of the x squared. So we're going to need a column for x squared. So we'll take all of the x values and square them, and then we'll take the sum of that column. We also need the sum of the x's squared, so that just means take the x column and add them all up and square them. We need the sum of the y squareds, so let's add that column in here. And then we need to take the sum of the y's and square it, so we'll add those columns. So I'm just going to fill in some values here. The xy's mean take x and multiply it by y. 1 times 2.1 is 2.1. 2 times 2.5 is 5. 3 times 2.8 is 8.4. 4 times 3.5 is 14. And 5 times 4.5 is 22.5. So that's the x times the y's. Now we'll do the x squareds. So again, here's x. We're going to square it. We'll square all of these. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and 5 squared is 25. And then the last column that we need here are the y squared. So here are our y values right in this column here. We are going to square these. So 2.1 squared is 4.41. 2.5 squared is 6.25. Where are we now? 2.8 squared is 7.84. 3.5 squared is 12.25. And finally, 4.5 squared is 20.25. So we need the sum of most, if not all, of these columns, so we're just going to add them up. So we'll start with the time column. We'll add up all of these values, the numbers 1 to 5 added together give us 15. If we add up this column, we get a total of 15.4. We'll see maybe in a later video about how it is very easy to do this in a spreadsheet, by the way. Here we get 52 as our total, 55 over here, and 51 over here. So let's go ahead and start filling in values for our formula. So I think I'll do that just over here because I think there's enough room over here. So r is equal to n times the sum of the xy's minus the sum of the x's times the sum of the y's, and that all gets divided by, now there is a square root here, notice the square root, so I'm going to jot that in here. It's not a very straight square root, but hopefully you get the idea. We've got a bracket here, n times the sum of the x squareds minus, now notice the difference here, this is the sum of the x's that get squared, so we add the x column and then square it. We're not adding the x squareds. That's the end of that set of the bracket, and then we go to the next set. N times the sum of the y squareds minus the sum of the y's squared. And we can close out the bracket. So let's plug in the values that we have. Remember that n is the number of data points. We have 5 of them. The number is 1 to 5. Count them up, there are 5 of them. So n is 5. The sum of the xy's, that's right here. So 5 times 52. Minus the sum of the x's. The sum of the x's is right here at 15. Times the sum of the y's, which is 15.4. And all of that gets divided by the square root. Don't forget that square root. Maybe I should extend this one a little bit so we can make sure we see it. Of n is 5. The sum of the x squareds, that's right here, 55. So 5 times 55 minus the sum of the x's squared. So the sum of the x's is 15, and we're going to square that. That finishes off that set of brackets, and then we'll continue on here with the second set. So 5 times the sum of the y squareds. Here's the sum of the y squareds, which is 51. We close that bracket, and then we're going to subtract the sum of the y's squared. So the sum of the y's right over here, 15.4. And we'll square that. Alright, so I didn't quite go far enough here. Ooh. Here we are. So I'm going to evaluate the numerator in the calculator. So I'll just do 5 times 52 minus 15 times 15.4. And if I do that, I get 29. And then I will evaluate the second part in the calculator as well. I'll even do the square root. We'll do it all in one go. So I'm going to type in the square root of bracket 5 times 55 minus 15 squared, and then close the bracket, times, don't forget there's multiplication in here, and then I'll just multiply by 5 times 51 minus 15.4 squared. When I do that, I get 29.866 with a bunch of other stuff, but you can get the idea here. So again, if I do the division here, I get an answer of 0.97. So that's my correlation coefficient, 0.97. That indicates, because the number is positive, that means that there's a positive correlation. If we were to graph this, we would see that the line slopes up and to the right. And that's 0.97 is close to 1, so it's not a perfect correlation, but it is a very strong correlation, and that's what the R value will tell us here. So that's how we can calculate the correlation coefficient. You can see that it's not hard. You know, the math is really just about multiplying some numbers, adding some other numbers, and then plugging them into the formula here for R. It is time consuming and tedious, which is why technology and spreadsheets can help us a whole lot here. One thing that I do want to mention here is the effect of outliers. I just want to talk a little bit about outliers. The outliers can have a very big impact on the strength of a correlation. So if we look at this set of data here, we can see that there's an outlier here, and maybe there's a reason for that outlier to be over here. It's quite far from all of the others, and when we do this calculation and see what's happening here, we actually get an R value or a correlation coefficient of let me just check here, of 0.887, I believe, with that data point in there, which indicates it's a strong positive correlation. The way I was able to tell that is that this graph was done in a spreadsheet. The graph or the spreadsheet can give us what's called an R squared value. We call that the coefficient of determination. And if we take the square root of this number, we will get the R value. So R in this case is equal to 0.888. 8, I guess, if you round. So that is the R value. Now, if we were trying to compare this graph to another one, and we wanted to say which one had a stronger correlation, this outlier might have a big impact. So we may actually want to take this outlier again and redo the calculation. And when we do that, the R value should increase, and we can make some comparisons there. So sometimes it's useful to do that. Sometimes maybe not. Maybe that point is representative of what's going on, and it should stay there. But if for some reason there's this crazy outlier, and I think if we're talking test marks, maybe for some reason you have a really, really bad day on a test and your mark goes down a lot, that outlier might have an explanation. Maybe it doesn't, and you just struggle, but maybe there's a good reason for you not having a good day and a good test mark that day. So it may be worth reassessing here. And when you do that, the R value, when you take out that data point, should actually be higher than this R value here. So I just wanted to point out what impact those outliers can have. And sometimes when you're analyzing data, it's worth looking at removing those outliers, especially if there's good reason to. So there's a summary of correlation coefficients, what they are, what they mean, and how to calculate them.